Okay, so in the last video, I basically derived Fick's second law of diffusion. And then I stated, though, that concentration gradient, right, if we look at Fick's first law, right, if I draw Fick's first law, J equals minus D um, dC dx. We can see from this that it kind of seems that the concentration gradient, right, is kind of what determines diffusion. But I said that this might not be the case, and so I'll provide some justification for this, right? So let's say we have a system. We have a system where we again have kind of that film, right? And what I essentially have is that I have some concentration um, called C1 naught, right? Which is one just stands for the species, not depending. The zero just states that it's at z equals zero in our coordinate axis. And I have another concentration on this side, right? And I'm talking about, I'm talking about this solution, the concentration in this solution over here, all the way on the right. And let's say that this solution has a concentration of 1L, right? What we would expect to see, noting that the diffusion flux is constant, is that we would expect to see a linear line, right? This is not straight, but we would expect to see a linear line knowing that the diffusive flux is constant. Well, there's actually one caveat in this system. This system basically assumes that the solubilities inside the film, right? Solubility here is the same of the solubility in the film is the same as the solubility outside in these solutions, which oftentimes in real life is not true, right? The membrane might have its own solubility. And so we can't really determine that. So let's say, right, the membrane actually has higher solubility, right? Let's say we have a system where membrane has higher solubility for the solute involved for species one. Well, in that case, what we would actually see is that we would see that somehow the concentration, since the solubility of the solute is more in the membrane, we would see that C1 naught actually jumps to here, right, inside the membrane, and C1L actually goes here. And so this is a problem, right? Because if I was to graph this, right, what we would essentially see, right, let me do this in blue, we would have a constant concentration, all of a sudden jump here, come down here, and then come down here, right? And so you might think, okay, well, what's the issue with this, right? There's this discontinuity here, right? And what this discontinuity over here implies is basically that concentration, right? We can have things moving against the concentration gradient, right? Because remember, big C 1 naught is actually less than small c 1 naught, right? So this is less than this. And so how are we basically getting diffusion if that implies that the particles must go up the concentration gradient, right? Because C1 naught has a greater concentration. How can we define this? Clearly, concentration gradient cannot be the determining factor for for driving diffusion. And the reason for that is actually this is a lie. That concentration gradient um, is what drives diffusion. What really drives diffusion is something called chemical potential. And so, what is chemical potential, right? Well, chemical potential is usually defined in thermodynamics um, as basically the point at which things reach particles in different phases reach equilibrium. And if I was to write that in a math form, right? So let me write that chemical potential. Very similar to kind of like voltage. It's like that's what drives um, charge, right? Moving. And so chemical potential is denoted by mu, right? And it's equivalent to the partial derivative of Gibbs free energy divided by the mole. So let's say I have a species B, and it's determined at constant T, P, and Na, right? And so this is not a thermodynamics tutorial. This is not a thermal series, and so I'll kind of briefly skim over what chemical potential means. But what it means is basically it's the determining factor um, for the stage at which a system reaches equilibrium. So just to quickly summarize what is going on, let's say I had a box, right? And I had evenly split. I have particles. I have particles A, and I have particles B, right? I have particle B. And particle A is concentrated on the left, particle B is concentrated on the right. I have a lot of A particles here, right? And I have a lot of B particles here. Perfect. And these are both dissolved in, let's say, some medium, right? In called alpha 2, alpha 1 on this side, and it's dissolved in um, alpha 2 on the right, right? And so alpha 2, alpha 1, right? So what you would, eventually expect to see is that we will see kind of the particles A will go on this side, particles B will go on this side. And we'll reach some sort of equilibrium where we have kind of some particles B here and some particles of A here, right? So what drives this? Well, the thing that drives it is basically the chemical potential of A in a certain phase must equal the chemical potential of A in a different phase, right? So to write that in math, what that means is that the chemical potential of A in a certain phase, alpha 1, must equal the chemical potential of A in alpha 2, right? And the same thing for B, right? Chemical potential of B in alpha 1 must equal chemical potential of B in alpha 2. This is what determines equilibrium, right? So if we were to look, people often say that, to give some intuition, people often say that, chemical equilibrium is reached when Gibbs free energy is at a minimum, right? You want to minimize the Gibbs free energy. So if I was to draw a graph, right, and I had Gibbs free energy, right, and I had the mole fraction, right? So let's say I had Y. You would see that we have kind of this kind of curve, right? And let's say that I kind of drew a line here. If I was to draw this system, right, initially, what we have is that we have, let's look at B actually. So I'll label this the mole fraction of B, right? What I would see is that initially we have a high mole fraction. This is in alpha 2. We have a high mole fraction of B in alpha 2, right? This is the alpha 2. And we have a low mole fraction of B in alpha 1, right? And so the way how you determine kind of um, the chemical potentials is to basically take a tangential line. So if I was to take a tangential line, um, let me draw this in dark. So if I was to, cut across, or blue, I guess. If I was to kind of like cut across this, right, and I was to cut across this, right, this denotes the chemical potential of B. I should read this in actually. Never mind. This is the chemical potential of B in alpha 2, and this is the chemical potential of B in alpha 1, right? This is caused by the tangential lines because remember the chemical potential is defined as the derivative of Gibbs free energy. And so what we can see is that initially these chemical potentials, right, in alpha 2 and alpha 1 are not equal, right? And so therefore the system is not at equilibrium. But if I was to go back, right, and I was to find where the Gibbs free energy is minimized, which would be at the bottom, right? We would see that if I drew a tangential line through here, right, it would actually equilibrate at some point, right? And that happens to be at where it gives free energy is at its minimum. And so this is the basis for where equilibrium can be reached. But mind you, this doesn't mean that the concentrations have to be equal, right? So in this curve, it looks like it might be around 0.5. But imagine if I drew a curve that looked like kind of like this, right? Then this would actually be where the equilibrium point is, right? And so this means that essentially equilibrium can be reached, but equilibrium does not mean that we have equal concentrations, is what I'm trying to say. All right, perfect. And so this also can explain why we have systems where things might spontaneously not want to be mixed together. It might spontaneously form its own separate phase separations. All right, perfect. So now that we understand how things reach um, equilibrium, we can actually use that to talk about this. Why are we seeing that we can have particles move from a lower concentration to a higher concentration? Well, it's because chemical potential determines the equilibrium, right? So what this means for this system is that, let's say we said that the membrane has a higher solubility of the solute, right? It has a higher solubility, and so the chemical potential in the membrane, right? The chemical potential, right, of let's say species 1 in the membrane has to be equal to the chemical potential in, let's say that this is solution, right? So solution. This is what has to happen. And this doesn't mean that the concentrations have to be equal. And so what we can see now is that we actually can have a system where the concentration goes from low to high and we still see diffusion, right? Because it only depends on the constant and on the chemical potential. The chemical potential is what drives diffusion. So then you might ask, okay, well, why do we use concentration gradient instead of saying chemical potential in the equation, right? Is Fick's law wrong? Well, no, because what typically happens is when we think about chemical potential, right? The way how chemical potential is calculated is um, we have this chemical potential, right? So let's say we have species A. That's usually the chemical potential of A at standard some standard temperature, pressure, right? Standard properties, plus RT times the log of concentration, right? Or actually, to be more specific, it would be kind of for non-ideal conditions, it would be like an activity coefficient times the concentration, right? So this is how we calculate the chemical potential. Well, as I said, this is a well mixed solution, right? It's well mixed, constantly stirred. And so what that means in terms of the solution is that we are minimizing any sort of interactions that would have a strong effect on the properties of the solution, or minimizing non-ideal interactions. And so when something is minimizing non-ideal, we're typically just trying to say that it follows ideal conditions. And so when something follows ideal conditions, an activity coefficient is essentially 1 for ideal, right? And activity coefficient is for liquids. Fugacity would be what we were using for gases. And so this basically goes away, and we see that chemical potential is essentially a function of concentration, right? And so we use concentration as kind of a proxy for what we're trying to say when we talk about what drives diffusion. And so concentration gradient is not saying that concentration gradient drives diffusion is not completely wrong, because in most cases we don't see a significant difference, right? So in membranes, right, this would have to have a significantly different solubility. But for most systems, when we're modeling them as ideal, concentration gradient serves as a perfectly fine proxy um, for why we might say that something depends on for diffusion depending on concentration gradient. The more important thing is that we can also measure the concentration. So it's more measurable, it's easier to measure, and so we can quantify it and really substitute it in. And so Fick's law is not wrong. It just uses concentration gradients as a proxy. So it's important to note the takeaway from this is that chemical potential, oh, I want to use the same color. Chemical potential is what drives diffusion. This is the main point. And so hopefully now you understand, well, what is going on? Why can we see these jumps and kind of intuit what is going on behind the scenes? All right. In the next video, we'll actually jump into equations that, or not equations, but problems that we can use to see how Fick's first law, second law can be applied in an actual scenario.